Okay, it's 3 p.m. I think we start with Alexander from Tempesta. And with the word.
Hello, my name is Alexander, yes, and I'm CEO at Tempesta Technologies. And we develop Tempesta FW, it's open source application delivery controller. And also we do custom software development and high performance network processing area and in database. Notable examples would be web application firewall, mentioned by Gartner Magic Quadrant. We made it for architecture of the product. And also, right now we develop a new feature for MariaDB by request of MariaDB AD. And the feature will be hopefully in mainstream in MariaDB 7.3. Right now we use a fetch actual version of the feature from our repository GitHub. So we started Tempesta FW by request of one of our customers. It was a huge web hosting provider. They actually wanted to protect huge web hosting against very complicated DDoS attacks. And especially they were interested about application-related DDoS attacks as the most complicated attacks to detect and prevent. And we started from patching engineers from trying other open source web accelerators, and we quickly realized that modern web accelerators are suitable for our tasks. So we had a look at kernel accelerators. They behave a bit better, however, they also didn't satisfy our needs. Basically, we realized that we need some kind of hybrid of a web accelerator and a firewall to be able to process HTTP as fast as possible and generate complex rules to work application layer attacks. So it must have very fast HTTP accelerator because we still need to process HTTP requests to fight against HTTP abuse and other DDoS attacks. It must have a very fast web cache to be able to mitigate DDoS attacks if we cannot find out all and work all the bots. Also, we need very strong network set to be able to fight against attacks with many concurrent connections, short-lived TCP connections, and so on. Also, advanced fitting, I also mentioned the FOSDEM. So we started from a hybrid of web accelerator and firewall. We were there and we moved to kernel space. During this presentation, I will put a lot of details about current problems with user space web accelerators and explain details why we moved to kernel space. So basically, first prototype of Tempesta was just a web accelerator, a firewall, and since usually web accelerators stay in front of huge server farms, we implemented several load balancing algorithms. As our development moved forward, we implemented more load balancing capabilities. We introduced several few logic to protect against web application attacks. And we also need to use SSL and implement it in kernel space because nowadays any internet application works using HTTPS. Data compression and connection quality to survive is still in progress. Basically, software and such products are named like application delivery controllers. And typically you find the mix of the functionality in boxes like F5 or Citrix. solution equal in performance to these proprietary boxes, and the solution is fully open source. Typical examples of Tempesta FW would be the same exactly as for any application delivery controller. So if you think about more performance and protection, for example, if it's not enough performance from Nginx or other web accelerator, then you might think about hardware box, for example, performance 5, to put it in front of your Nginx or Varnish file and protect and accelerate your content. And typically this use case is also used for Tempesta FW. It can be used in massive CDNs, content management systems, shared hostings, and so on. A lot of use cases. So we started to discover what's wrong with nowadays web accelerator architecture. So the first thing which we did is was to put some DDoS root on Nginx. And surprisingly, we found that Nginx spends a bit more time to work malicious requests rather than services from static file. Basically, we use a very small static file, and usually you will see different picture if you use large dynamic content and have dynamic logic. But anyway, we think it's unacceptable to spend a lot of resources to work malicious traffic because we have just a lot of requests from DDoS bots. The problem with Nginx is its very limiting model. Basically, when you need to service static content and block malicious requests, you do exactly the same logic. You must still send error response to new malicious file which you just observed. However, you must run additional logic which is implemented in rate limited model. So the limited functionality in Nginx introduces additional logic and additional complexity which takes this 1 extra microsecond. So to cope with the issues, people usually configure Nginx not to send error response to broken clients, and sometimes they use some log passes like fake1 to process Nginx access logs and generate in runtime repeatable rules. However, the technology based on parsing and writing text file looks like 50 years old. It's not fast, and sometimes people recommend to just switch off access logs for better performance. So, it seems I have issue with slides. One might think about writing a Nginx model which will generate rules, IP table rules on the fly. However, generate coupling web accelerator with a firewall is not the whole story. And actually, we have a lot of issues with web accelerators. Actually, any modern web accelerators were designed to deliver content in normal circumstances. So in most cases, they deliver perfect performance for you. And most of the cases means that your clients are innocent, good clients. However, web accelerators like Nginx provide some filtering, and we just saw that filtering is not so fast as it should be to defend application where DDoS attacks. And also, all the servers are basically designed in early 2000s, when we had an issue to handle 10,000 connections concurrently. It's not a problem to generate 10,000 or 100,000 connections for DDoS botnet. And actually, DDoS is always about corner cases. It means that if your system has a bottleneck, for example, establish SSA connection, then an attacker can generate exactly attack against your SSA handshake. If you're not so fast to handle small packets, then attacker can generate flood with a lot of small packets. So DDoS is always about corner cases. And we started in our project to be reliable and stable against corner cases. So we can deliver stable performance regardless of normal flash calls, audience, and DDoS attacks. So as we analyze it, kernel mode web accelerators behaves a bit better because there's no context switches and so on and so on. However, modern systems, modern operating systems, and modern CPU architectures provide very nice features like zero copy and lazy TLB, which makes context switch very cheap. And kernel accelerators now are dead. However, I will show that if we think about hardware solution which can defend against DDoS and deliver stable performance for normal operation, we still need kernel access. One of the huge problems which is now addressed by Facebook, and Netflix is TLS. Basically, if you need to send your content through encrypted connection, you must to copy the file content to user space, and after that you encrypt it and copy again to transmit the content to the encrypted socket. So the guys try to move only encryption part of TLS to kernel. So now we can use the similar interface to send file and send encrypted content without copy. However, TLS handshake remains in user space, and it's vulnerable for DDoS attack in handshake. So that's why we move it full TLS into the kernel. If we think whether we can take one web server, modern web server, and optimize it and develop further such that it will deliver more performance and will be capable to defend against large DDoS attacks. The answer is not. There's a trace profile for Nginx and simple HTTP boot attack. And we see that the most hotspot is HTTP parser. We also have some copying and network I/O rootedness. And finally, this late living logic takes also the good place. SSH is top 10 of most hot calls. And we see that the file is actually flat. It means that there is no single point of which we can optimize and increase performance of the server in 2 times, for example, or in 3 times. It means that if we need to make a solution, for example, 3 times faster, we need to develop the core architecture. We need to remove the slow I/O, we need to remove copying, and so on. The problem with user space accelerators are also system calls. They're surely cheap in nowadays system calls. They're still not for free. Typical request handling takes about 9 system calls in Nginx, and we can eliminate only one of them if we disable access log. By the way, so far I'm talking about Nginx. However, most of the things which I say are also applicable to other web accelerators. Nginx is just an example which we started from. The other problem is web cache. A lot of web accelerators still use old-fashioned part system-based databases, some kind of databases. because they generate keys in the database using hash on URI and host header. And the funny part begins that you see that there are short directory names, and we have a hierarchy of 2 layers. And the things are done to cope with slow file system operation. Actually, to find a file in file system having thousands of files is extremely slow operation. File open system calls extremely slow because it requires net lookup and requires disk access. So engineers uses cache of open file descriptors and show you the cache mitigates the problem. However, it's not about stable performance, so you can easily get DDoS attack which will just iterate over all your available resources. So your cache will be efficiently evicted, and you will run without cache, and you use the plain file system on each request. That's a simple case how we can kill such web servers. So Apache Traffic Server starts to do more clever things, and they implemented some kind of database to handle web cache. So we do the same. Also, this very HTTP header, which actually requires a secondary key in terms of traditional databases. The problem is, if you have some content which can be delivered, which can have different versions, for example, for mobile clients at the bottom and desktop clients at the top, and you want to send different content to different devices. Content has the same URI and host, so it stores in the same file, in the same file system. And you need some kind of secondary key to differentiate web users from desktop users. So you use the secondary key, and if query specifies user agent, then you can take care about user agent value and generate different content for secondary key. So all in all, we need a real database to efficiently handle web content with stable performance results. The next thing is HTTP parser. As we just saw, HTTP parser is a hotspot under DDoS root. And surprisingly, most of HTTP servers use old-fashioned dummy approach to process HTTP. This example of parser state machine. So we have a while loop with a switch statement, and now we have state variable with value. Again, we have value 1, we have where the state 1, and we have input character B. So we start from checking state variable. We move to proper state with corresponding to proper character, and we assign the value to state variable. Next, we move to end of while and switch statement. Keep in mind that at this point we fetched at least 3 cache lines of code cache. The first cache line we fetched at the beginning of while and case statement. The second line we fetched at processing case B, where we assigned value to the state variable. And the third line is fetched right now at the end of the loop and switch statement. Now we move to beginning of the loop. We start to check state variable again, and finally we go to state 2. If we look at the picture and try to understand what's happening, we see just a lot of spinning around the code. Reason at state 1 and giving chapter B as input, we know precisely where we need to go. In this case, we can just fetch the next instruction. We don't need any jump at all. So our CPU prefetcher will work perfectly. If we would be in state 1 and case A, we need to jump, but we again know exactly where we need to be. We actually do not need the dummy state variable. We don't handle it, and we can save a lot of logic. This parcel is actually generated by Rage code generator. And we do apply the same logic in our parcel, and we also split set of states in different pieces to generate a slow switch jump table as possible. So we apply different optimization strategy to make the jumps and processing as fast as possible. Well, HTTP is actually a text protocol. This in version 1.1. So you can easily get very large strings. It could be a cookie. We saw with the agent about 65 kilobytes in size. It could be cookies, URIs with the agent. So sometimes you need to process very long strings. Since we have AVX2 CPU extension for about 3 years, HTTP still doesn't use the extension in their string operations. Moreover, HTTP strings is a very special case. There are different points which makes HTTP strings special, and they are all important in optimization of string processing in HTTP case. The first one is that actually we do not need to treat 0 byte in a special way. Actually, we have several binary codes in ASCII, and we should treat 0 byte the same way. Secondly, there are special delimiters, and CRLF makes a real trouble for us, because if we are creating zero-copy fashion, CR will be in one packet, LF will be in other packet, and we have to keep finite machine states between the receiving the parts of the delimiter. Also, some basic wires sense just the LF as a wire terminator is down, so we have to handle the terminator the same way. In HTTP path, when you put your own HTTP path, you definitely have some static strings. For example, it could be names of HTTP headers which you want to process in a special way. For example, host header, user agent header, cookie header, and so on. So these names are encoded in HTTP path directory. So you have constant strings. So when you compare input string against this constant string, you don't need to convert case of the second string. You need actually only one case conversion for input string only, and you can save necessary iterations. And in that case, CMP converts strings of both cases of both of the strings. If you need to validate input string against the word alphabet, you might think about using str-spn to accept or reject some alphabets. And this is a bad idea because str-spn spends just incredibly many resources to compile, accept, or reject sets. Basically, HTTP has only several word alphabets for different HTTP headers and URI, and you can encode the sets directly in your HTTP parser. In some of modern HTTP servers, there are attempts to do strings processing like matching HTTP header names using finite machine, as we just saw in previous slide, and the performance of such parsers are very, very slow. The last thing about modern web accelerators is network I/O. Actually, we can consider an example on the slide. There are 3 packets, and let each packet contain full HTTP message. So, firstly, we read the packets in software queue, and software queue places the packet in input queue of sockets. After that, software queue wakes up process owning the socket, and process starts to copy the data from kernel to user space, process HTTP, and do some other logic. When process finishes with first socket, it can find the packets on the second socket already out of the cache. Actually, DCA technology, direct cache technology from Intel shines in this situation. However, DCA places network packets in layer 3 of CPU cache. However, if you want to process 10 gigabits network traffic, layer 3 cache will be not enough to wait while user space process pass HTTP, copy data, and so on. So in Tempesta, we directly built in HTTP parser into HTTP IP set, and all the packets are processed as soon as possible, while all the data in CPU cache. All the issues which I just mentioned are listed in Tempesta FW, and this hybrid of HTTP accelerator and the firewall. Actually, it's multi-layer firewall because it uses firewall rules and IP layer and HTTP layer. It's directly embedded in this HTTP IP set, and we ship built-in filters to fight against layer 7 DDoS and web application attacks. As I told, we employ faster HTTP parser. We have specially designated in-memory database, which is malware and highly optimized for modern hardware. Have advanced load balancing schedules, and I will cover the topics in the next slides. I want to start from benchmarks. Benchmark results and description. How do we do the benchmark such that you can reproduce the results? You can find them in our wiki. And the slide shows that we can reach 1.8 million requests per second on 4 cores CPU. It's one of the cheapest CPU. If we analyze the performance result carefully, basically this is somewhat 3 times faster than well-tuned engineers can reach on the same CPU. We should be much more faster in the DDoS condition because we have that integrated firewall. We can work quite more faster than any engineers processing while using rate limiting, failure one, and so on. However, it's basically very difficult to produce DDoS logs. I mean, it's very difficult to emulate DDoS workload in test labs. For example, we have about 3 servers now test bed, and real DDoS is not possible to emulate in this environment. The next interesting result is about popular user space HTTP sets. And one of the examples of HTTP servers implemented on top of user space accelerators is CStar. Basically, it's not so clear for me from their performance benchmark whether they whether the 1.3 million requests per second for 4 cores or 4 hyperthreads. But either way, CStar bit slower or bit faster than Tempesta FW. So basically, basically, we are comparable in performance for normal TCP processing with good user space TCP stairs. However, we do not have drawback of such approaches because Tempesta is actually Linux. It's built into Linux kernel. It's probably, we can argue about this approach, probably it's not so good. However, we fully integrated with any Linux utilities. For example, if you need to write some IP table rules, and the graphic which is passed to Tempesta FW will be fitted by IP tables. Go ahead and do that. If you need to run speed up and analyze graphic processed by Tempesta, you still can do that. You can use graphic control to distribute graphic, to control graphic which is passing through Tempesta and so on. So basically, if you need to do such things in user space TCP step, you either must re-implement them for user space step, or you need to use some dummy interfaces with hopping and additional overheads. So our approach is, yes, we know that growing creating system is not good, but we argue not to copy code twice. It's not good for operating system world to execute 2 copies of TCP/IP stack on the same system. If you need to go further, then you need to run 2 firewalls on the same system. You need to run 2 Linux virtual servers and whatever. You just do not copy and redo, rewrite the code rewritten by smart creative system developers. Also, I want to mention that while there are a lot of TCP/IP steps implemented in user space, you can imagine how large TCP stack is. And basically, a lot of user space TCP stacks do not have good extensions like selective acknowledgements, different TCP congestion control algorithms, and so on. So actually, TCP/IP stack of Linux is good and fast, and we can deploy it, and we can live with it. Let's have a look at Tempesta architecture. So if we have packets going to network adapter, we check it against our rules and way of theme. Next, we process it in HTTP parser and run analyzing model type space and analyze already parsed HTTP request and apply HTTP rules against it. If it decides that the request is malicious, it will generate a new rule which will be put to way of theme, and we will just block the request. If the request is good, then we can pass it to upstream or reverse to our web cache. As I said, we use common sockets. Since we live in Linux kernel, we do not use file descriptors, we do not use input queues, and so on. So there are no locks. However, the case why user space HTTP accelerators are slow, while we still see very good numbers for user space HTTP, is that real-world TCP server must solve different issues. One of the issues is proxying HTTP requests. In this example, we have 2 sockets. First one is client, the second one is server socket. We have 2 CPUs. And basically, if you have a bidirectional connection between client and server, client sends new requests, like using HTTP pipeline and server responds to various requests. Then you might want to take log of TCP control blocks in different order, and you easily can go to that log. This hard thing we still need to solve it using user space TCP stack. And in our project, we use CPU interconnection. Actually, Gospel. We use in buffers per CPU. And if we consider traffic from client to server, first the package is processing on per CPU control block. Now we have no locking because all TCP control blocks are bitted to local CPU. So for a CPU cannot access to local sockets. So first we process incoming packet on the first TCP control block. Next we place request to read buffer of server socket, and CPU which handles the socket will do actual transfer to server. So there's no locking. We have great performance on index traffic and low latency for web. So also we very good if you need low latency HPC device. We did preliminary performance measurements in 2015 of synchronous circuits. We see that the blue line of synchronous circuits much faster establish new connection in comparison with user space sockets and ever kernel space sockets. Also, we have more stable and more performance in processing TCP packets, also compared with our other kernel sockets. I already said about HTTP processing. You can find algorithms about HTTP parser and particular strings processing in our blog. And now just a few numbers. We bit faster than Nginx in 1.6, 1.8 times in short HTTP requests. However, if you go to long strings, for example, with large cookie or URI, it's something about 1 kilobyte. It's not so large cookie, not so large URI. The URI cookies of such length is very common nowadays. And our string processing can be faster in 3 or 6 times the libc and user-space implementations. We also use dedicated web cache. It's basically on top of NUMA-aware architecture. NUMA-aware means that we can copy data on new nodes to be able to survive requests from local NUMA node, or we can do sharding computing, which node will respond. And we use our own unique algorithms that is structured to for FOSDEM index in the database. Basically, it's based on modern research, cache conscious data searches. And the core idea of the data search is that we have an array of very short offsets in one CPU cache line. So we have 16 cache lines. If we want to find some string, we calculate cache value, and we use less significant 4 bits. Since now we have no data, we just allocate new data page and place data in it. If we find that our data page is full, we have a lot of collisions, then we parse the node. During the parse, we allocate new index node, which resolves second 4 bits, and we have to split our data page. And this is the only place we use logs. Any other places, operations with data structure are log-free. So basically, Tempesta provides several limiting functionality for DDoS attacks. You can also defend against low HTTP attacks, specifying time limits and chunk numbers. It's basically very hard to do in user space because you do not control the network packets. Also, you have a protection against several web attacks. For example, HTTP response splitting. We account carefully HTTP requests and responses. Basically, we constantly grow in our set of filtering logic. However, we do only very fast logic. If we feel that we need to do some complex logic, for example, to process XML in responses or something like that, we leave the logic for user space web application files. So the point of Tempesta is just to learn very fast logic and quickly analyze the graphic. We have also load balances. I would say probably some of them are known. For example, the Tempesta's hashing is stable to failover. We use machine learning technology in predictive and predictive schedule. We analyze how quickly server replies to a request and build trends against it. I would skip example configuration. We have sticky cookies to fight against DDoS, which are unable to solve cookie challenges and provide sticky session-specific scheduling. Prerequisites are clear because we use modern CPU features. And finally, I just want to address some of questions and concerns about the project. Firstly, Tempesta is a very small piece of project. It's much smaller than any modern file system. We do not try to move any logic from HTTP accelerator to the kernel. Moreover, we are going to deliver fast transfer to user space of parsed HTTP messages. And typically, we'll deliver web application firewall which is more capable with assembly functionality in user space. We use best practices in Linux kernel development. You can find our pull requests and code reviews at our GitHub. We will deliver packages, so you don't need to build kernel and Tempesta by hand. So as a result, conclusion, Tempesta is always very good if you need a lot of performance when traditional HTTP accelerators are not enough for you, and when you need to defend efficiently against various DDoS attacks. So thank you. Our site is powered by Tempesta FW for 9 months. We didn't see any failure during the time. Availability is at our GitHub. Any contribution are very welcome. And you can find algorithms and so on at our blog. So thank you for listening. Just a few minutes for questions.
Do we have a question, please?
No questions.
No one from the audience. So this is available and compilable to the kernel, or your code is available, as I see, and it's compilable to the actual kernel version.
Yes.
As you see, your site is powered by your own product, obviously.
Yeah, actually, we have a patch in for Linux kernel. You can download it from our GitHub, and we have a kernel model. So it's not in Linux mainstream so far. Hopefully, we will be in the mainstream some time in the future, but not now. Did I answer your question?
Yeah, thank you. Some more in front. No questions anymore. So thank you very much.
Thank you.
For having here. It was very interesting. Maybe applause. One more.